Hey guys, let's talk about gravitational torque and the center of gravity. All right, so what is gravitational torque? Okay, let's get to answering. This is torque caused by gravity. And why don't we talk a little bit more about gravity, all right? So, when gravity, and I've said gravity a lot in the last 10 seconds, when gravity acts on an object, on an object, it acts on every particle that makes up that object. All right? So imagine if our object is a human being. All right? Let's say it's skydiving, is in free fall. So this is right before he pulls up his parachute. Gravity is gonna act on every single component, every single particle, not component, sorry, on his body, every single place, even the spaces in between the arrows that I've just drawn. Yeah, so gravity acts on every single particle. All right. Now, when you want to analyze this system, this can be a bit tedious. So, mathematically, there's a proof that tells us that we can pretend as though gravity acts at a single point on our object. So how would that look? Well, boom. Yeah, these are all weight vectors. And this makes our analysis a lot easier. All right? In AP, you're not required to mathematically prove this, but this point where we can pretend as though gravity acts like most of the gravitational force is acting at at a particular point is called the center of gravity. All right? This point is called the center of gravity. All right. So, this is an example. I wrote a small paragraph for you guys. So the center of gravity is a coordinate point on an object that you can assume all gravity acts that on there or on that particular point. So if we analyze this lady who's a gymnast, swinging about this pole, to calculate her gravitational torque, and this is just torque due to gravity. So just a small primer on gravitational torque. So gravitational torque. So we know our regular torque is F times R. In our case, gravitational torque is just going to be weight times R. So that's the gravitational torque we're referring to. Anyway, so to calculate our gravitational torque, we can calculate it with the premise of the center of gravity coordinate. All right. Our R doesn't have to be our r from each point on the person's body. Instead, we can use the center of gravity to calculate her gravitational torque. Okay. So a quick example. Let's say we have a stick or a flagpole, if you like, hanging from a cliff. Oh, ah, I gotta go on D&D. Sorry. Okay. So, if we have our weight vector, our center of gravity, a particular distance from the pivot. So this is our pivot point. Yeah, we don't need to pretend as though our we don't need to act as though our weight acts on every point on the stick. We can just say our weight acts on at the center of gravity. Our weight acts at the center of gravity. So we say r 1.6. So that's from the pivot to our weight vector. Theta is 25 degrees, and mass is 3.2 kg. So how do we calculate torque? We use the torque formula. We have two ways of doing this. You can use the moment arm, or if you want, you can use the perpendicular force component. But in this question, the moment arm is very easy to view. And in most questions involving gravitational torque, you want to use the moment arm. So if I draw my line of action, and my line of action is just a straight line through the force vector, my moment arm is from my pivot to, let me change the color to make it more visible, from my pivot to the line of action. And this is my r perpendicular, or my moment arm. All right, but this is the moment arm. Moment arm, if you like, lever arm. Yeah. So now I can calculate my torque freely. So I need to first find my perpendicular component of r. How can I do that? Well, it's the triangle. I can decompose my vector. Let me check the cosine. It's just like cosine. So my cos theta is my adjacent over hypotenuse. Adjacent over hypotenuse. Adjacent is going to be r perpendicular, and times r my hypotenuse. I can cross multiply to solve for it. Get cos theta. All right, so I have my r perpendicular. So my torque. Oh wait, and what's my force? My force is gravity. F is going to be equal to gravity. So what's that? That's mg. So my force is literally, my torque actually, is literally going to be mgr cosine theta. And we know all these constants. So m is going to be 3.2 kg. G is going to be 9.8. R is going to be 1.6. And cosine theta is 25. And yeah, plug it into a calculator, and that's your torque. Approximately, this is about 45. You could use, that's using the moment arm. You could use the force arm too, but it kind of requires a bit more trig and geometry. To find F perpendicular, you need to decompose this into omega y and omega x. So, and then you will see that the perpendicular component is omega y. You get the torque is going to be omega y times r, and omega y is be equal to omega times cos theta times r, and weight is going to be mg cos theta r. It's the same thing, but it just requires a bit more trig. For me, I'd often just gravitate to the moment arm than doing the trig. So, yeah. Anyway, so there will be times we'll be asked to find the center of gravity. All right? And it's a key characteristic about the torque of a system that will help us find the center of gravity of a system. All right? So, what's the characteristic? Torque is always 0 at the center of gravity. All right? So if I have my quick example here, I have a pivot and weight 1, weight 2. It looks pretty balanced already. But for our purposes, let's say weight 2 is bigger. Let me just make that clear. Weight 2 is bigger. So it's kind of, and then now we're asking ourselves, where should we put the pivot in order for it to balance? So the place which put the pivot for the system for this dumbbell here to balance is at the center of gravity. All right? So, yeah. So now, how do we find that particular coordinate point? Well, we know this fact that we just mentioned a few seconds ago. The torque is 0 at the center of gravity. So my first step will be getting the net torque of the system. Change color. Torque 1 plus torque 2. Yeah? Now, I also need to have a coordinate system. So if I say my pivot is currently at 0, right? 0, and it's going to be my positive, my negative, right? If it's a number line, basically. Like right now, my pivot is at this 0, positive side, negative side. Yeah. And this is just for visual purposes. You don't need to draw a whole number line. I just want you to visualize what's going on. So my torque 1 in this case will be omega 1. I see omega. Look, omega 1 is trying to, or weight 1 rather, is trying to take my system in the clockwise direction, in the clockwise direction. So it has to be negative. And my R1, the distance from the pivot to omega 1 is positive. So it's going to be R1. All right? And my torque 2. Torque 2 has a weight 1 wants to take me counterclockwise. But my R for torque 2, my R for torque 2 is in the negative direction. So my whole system, so this is going to be negative as well. So now, my torque is always 0 at the center of gravity. Right? So my net torque, if I want to find the coordinate point, my net torque will be 0. It's going to be minus omega 1 R1 minus omega 2 R2. Right? So now, R1 and R2 are basically directions, right? And if I'm analyzing this dimensionally, I can call this my x-axis. I'll just call R1 x1 and R2 x2. So So 3 is going to be omega 1 x1 plus omega 2 x2, right? Like basically I'm saying the distance from here to here is x1, and the distance from here to here is x2. It's the same thing that I'm doing. All right? But we want to find the center of gravity. We don't know where it is, but we know it's not towards the end necessarily, or it's not necessarily at 0. So hence, instead of having our R1 is just x1, I'm going to rewrite this equation. So R1 is going to be x1 minus x CG, CG for center of gravity, minus omega 2 x2 minus xCG. All right. So now, what this allows us to do is, because the torque is 0, it allows us to find the point at which our system will balance. All right. And that point is xCG. All right. I can get rid of the negatives by dividing the whole system by -1. So I get 0 equals weight 1 x1 minus weight 2, weight 1 x1 minus xCG plus weight 2 x2 minus xCG. All right. And then I know weight 1 is equal to m1g, and weight 2 is going to be equal to m2g. So I can plug those in. 0 is equal to m1g x1 minus xCG plus m2g x2 minus xCG. All right. And keep in mind here, I'm trying to solve for xCG in the end. So again, I can divide this whole equation by g to get rid of the g's. The g's don't matter in this scenario. It's going to be 0 m1 x1 xCG plus m2 x2 minus xCG. Yeah. So now I can factor them in. I can factor everything in. m1 x1 minus m1 xCG plus m2 x2 minus m2 xCG. I want to solve for xCG, so I can take all the xCG terms across the equal sign. I'm going to have m1 xCG plus m2 xCG. It's going to be equal to m1 x1 plus m2 x2. So from here, I'm gonna factor out xCG. Let's call this m1 plus m2. It's going to be equal to m1 x1 plus m2 x2. Oops. I can divide both sides by m1 plus m2. And then, voila, I got my formula for my center of gravity. Beautiful, isn't it? It's for the x direction. In the y direction, it's the same thing. m1, instead of x, you got y in the y direction. Yeah. And if you got more masses, you can just simply add whatever masses you have. as so on and so forth. And that's how you find the center of gravity coordinate. So, yeah. Here are my last few words on the center of gravity. When the pivot, right, we have our pivot here, is above, right above, which is a straight line away from the center of gravity, torque is 0. All right? All right? So, when the pivot is right above or below the center of gravity, torque is going to be equal to 0. Why is that? Well, that's because the perpendicular component of the force will be 0. All right? So if we calculate even the perpendicular, the lever arm or the moment arm will also be 0, because you're right at the pivot, and to draw the lever arm, you need to draw from a point from the pivot to the line of action, and in this case, our line of action is right through the pivot, so that's going to be 0. So yeah, basically that's why the torque is 0. If the starting position is of an object that's so to say dangling, like this pivot here, and is in free fall, it will come to rest when the gravitational torque is right below the pivot point. When the center of gravity is below the pivot point. All right? And if the center of gravity is below the pivot point, it's going to be 0. So this statement here and this one, really important, but so are these two. So yeah, anyways, a quick summary. Yeah, gravity acts on every particle that makes up an object, but we analyze our systems as though gravity acts at the center of gravity. Problems in gravitational torque normally favor the moment arm to find magnitudes, but it doesn't really matter really. The center of gravity formula is x cg m1 x1 plus m2 x2 over m1 plus m2. Y cg, y center of gravity, same thing except y's instead of x's. And here I have just a small statement. I say in AP we assume that all objects are in a uniform gravitational field. However, that's not true, but it's useful to think in this way. Why? Because in a uniform gravitational field, in a uniform, I said universal earlier, sorry, I meant to say uniform. In a uniform gravitational field, the center of gravity equals the center of mass. And that's the video. I know it was a bit long, but yeah, I hope it was educational. See you guys. Bye.